Alright, so this time we are going to do boot algorithm and we are just going to go through the methodology, no background knowledge or anything else. So the boot algorithm goes like this. Usually they'll give you two numbers, right? And usually you have to choose one as your multiplier or multiplicand. What you choose as your multiplier or multiplicand doesn't matter, mostly, right? But it's usually safe to put the signed one as your multiplicand, right? And the negative one as your multiplicand and the positive one as your multiplier, right? So that the whole process will be a bit easier, but usually doesn't change. So for example, for the first question, they said we should do 6 times 6, right? Now here's the solution. So we start with this. 6 is equivalent to 0110. I'm sure you can do that conversion. And so our multiplicand is what 6. And our multiplier is also 6 because we are doing 6 by 6. Don't worry. Bad choice of numbers. Probably change it next time. So the first step for the boot algorithm is you have to first encode your multiplier, right? So our multiplier is 0110. So you have to encode it. Encoding means that start by attaching 0 to the end, right? And that's what we have done. So the original thing is 0110. But if you attach 0 to the end, that's the encoding process. Next, we have to go through kind of an initialization, and that's what you do at step 0. So step 0 for most of the multiplication algorithms, even some division algorithms, is just initialization. And initialization is this. You just need a table in this manner where you label your cycle, you label your Q0 and Q1, Q1, Q minus 1 bit. I'll explain that. You have your sign extended you have your action, like what you'll be doing, then the partial product, and you have your accumulation results in P. So here's what each one means. The cycle tells like the step we are on, right? Now the Q0, Q1 minus 1 bits is saying take the last two bits, right? And that last two bits will depend on where you are fetching the algorithm. Then the sign extended M is a bit tricky, so take notes. When your multiplicand starts with 0, right? When your multiplicand starts with 0 and you are sign extending it, right? Then you have to pad with zeros to make up for the architecture you're using. So for example, here we are using an 8-bit representation, right? Usually you use a 2n-bit representation, right? So if you are given two numbers which are both say 4 bits wide, right? Usually you use a 2n bits which is 8 bits representation usually for both algorithm because there's the expectation that after multiplication we'll have an answer which is 2n bits wide, right? Generally for multiplication. Sometimes it may be less, but usually for multiplication, that's what occurs. So, since we are expecting 2n bits, right? But our original thing is only 4 bits, right? We have to sign extend, right? So sign extend means that look at the very first bit. It's a 0, right? But we need to make this into 8 bits. How can we make this into 8 bits without changing its value? It's simple. You have to what? Put zeros in front of it. Zeros in front of a number doesn't mean anything, right? So that's what we do. We put zeros in front of it. So we put the number of zeros that will match up with the the number of zeros that will match up with the time extended version. So this we want 8 bit. We will put what? 4 zeros more so that the 4 zeros join with this 4-bit version will give us 8 bits. And that's what you see. Then there is a register which you call your partial product register. That's like a temporary register where you'll be storing the temporary results before you go and add it in the accumulator, right? And that one is also 8 bits. Then we also have an accumulation of the partial product in P. Yes, P is the product register. That's where your product to go to. So that's cycle 0. In cycle 0, basically we do nothing apart from initialization. So you see that the action box here is empty. Then we move on to cycle 1. Cycle 1 is basically a partial repetition of cycle 0. So cycle 1, we watch um what are the first two bits? the first two bits is what? This one, 0 and 0, right? 0 and 0. Now, the sign extended M is still there, so that's what you see. But you realize that um, there is a table called the boot encoding table, right? Which will show you for the various combination of bits what the algorithm expects you to. So you can see the table shortly. Um, yeah, so that's the boot encoding table, right? We'll be using it more often, so I've made it a duplicate. So yeah, so that's the table. And the table says that if the two bits you are considering are both zeros, then do nothing to the product, right? And the P raised the power key is just the product after k iterations, right? So don't be bothered. If the two bits you are considering is 0, 1, then you are supposed to add the sign extended multiplier, a multiplicand to the product. Those two are bits. Yes. And if it is 1, 0, you are supposed to subtract the sign extended multiplicand from the what product. If it is 1, 1, you have to do nothing, right? So that's exactly what you are going to do. So you realize that the first two bits. Now, when we are reading this, we read from the right, from the left to the right. So it means that we are reading like 0, this 0, and this 0, right? That's what we are taking. So you see, the action, we do no action. And the partial product, when because I'm multiplying by 0, we do nothing. And at the end of the day, we get 0, 0, 0 in the partial product register. And there is also, when you add this one to this, you get the same thing. Now, the algorithm requires that after every cycle, we shift left 1. So after we are finished with this step, then this step in the very same cycle, right? We shift left once, and that's what you see there, right? Now, I believe shift left is easy. So shift left means that it is an arithmetic left shift, right? So shift left means that you just take the first bit off, right? And since it's an arithmetic left shift, you have to append the zero at the back, right? So that's a left shift. Then we go to cycle 2. So cycle 2, we are going to consider the next pair of bits, right? Remember, when we did cycle 1, we use this 0 and this 0. Now, since we are done with cycle 1, right, we are not going to consider this 0 anymore. Now, for cycle 2, the two bits we are going to consider is what? The last two bits, which is 1 and 0. So we read it this way from this 1 and this 0, right? And that's what you see here, 1 and 0. Now, that 1 and 0, we'll still repeat our sign extended M, right? And the sign extended M we'll use in the next cycle is the one which we obtain after we have shifted in the previous cycle. So just see they are the same. Now the boot encoding says that when we see 1, 0, we should subtract, right? So here we are doing a subtraction, and don't be bothered, it's not scary. A subtraction is you to subtract one number from another. It's just to find the two's complement of the number and add it to that, right? So the algorithm says you are supposed to subtract the multiplicand from the product, right? So you are supposed to subtract this number from this number, right? Now, to make the whole thing easier, we are going to just do an addition. And how do you do an addition? You just find the two's complement of this. And by now, I hope two's complement is okay. So find the two's complement of this, and the two's complement of this will give you this, right? So that's the two's complement of it. That's the two's complement of it. And when you finish, so that's the two's complement. So you found the negative, right? So you just add it to the one in the accumulator, just the previous accumulator, and that will give you this one. Um, Same procedure, nothing has changed. Now, the algorithm says after every cycle, shift the what? Sign extended M once. So that's what we do. We shift it left once. So when you shift this one left once, you get this. Now we go to cycle 3. In cycle 3, the same procedure. We go and check which two bits are we now considering. We are done with what this bits. Although we use this one in the previous cycle, at every cycle we just delete one bit. So just take note. So these two bits, and so we are not considering these ones, but we are left with what 1 1, right? So we take them 1 1, and that's what you see here. So 1 1, and taking them 1 1. The boot encoding says what 1 1. We should not do anything. So we should just add 0. So that's what you see. We don't do anything, right? But our product register remains the same, right? But after every cycle, shift left once, and that's what you see. After every cycle, shift left once. Then we go to the fourth cycle. The fourth cycle is practically the same. We realize that um at the end of the day, we are also done with this one. So we left with what? These two, right? 0 1. 0 1, the boot encoding says we should what? We should add. So that's what we are going to do. We'll add. So that one, you realize that we are not subtracting, so there's no need to find two's complement, right? So what is in the multiplicand register? We'll just add it into the what? To the what? Product register, right? And that will give us this one. And that is all. You are done with the boot algorithm. So you can check your answer. This one is 36 right in decimal. So that's your answer. So 6 times 6 is 36. So our answer is correct. Now let's try a last one. And this one we are going to use -6. So the same procedure. Positive 6 is 0 1 1 0. -6 is what? 1 0 1 0. Now I told you choose your multiplicand. Yeah, I chose my multiplicand as the what 1 0 1 0 because it was negative, and I chose my multiplier as 0 1 1 0, right? Because it's positive. We check the positive or negative by checking the first bit. The first bit is a 1. It's a 1 here, so it's negative. The first bit is a 0, so it's what positive. Then we start with the process. So cycle 0, like we did in the previous one, initialization. But here the only catch is that because we are sign extend and here is negative, the first bit is 1. We sign extend with what 1. That's all. Then in cycle 1, you realize that we'll be doing the what first two, so 0 0, right? 0 0, we don't do anything. But after every cycle, we have to what shift left. So that's what you see. Then in cycle 2, realize that we'll be dealing with what? 1 0, these two. So in cycle 2, we'll be dealing with 1 0, right? But 1 0, the encoding says what? We should subtract. So try to subtract. And subtracting means we have to find the two's complement of this and add it to the product register. So the two's complement of this is what you see here. And now when you add this one to the product register, that's what you see, right? Then the next step, and after every cycle, they say you should shift left once. So the next step, we go for the next. So the next we've done 0 0, we've done what 1 0, and we've also done. We are now come to do what 1 1. So that's what you see 1 1. 1 1. They say we should not do anything, but after every cycle, they say we should shift left. So that's the rule we've done is shift left. And the last one is you have 0 1, as you can see. Remember, we've done what 0 0 these two, then we came to do these two 1 0. So you are now come to do these two 0 1. So that's what you see. So 0 1, they said what we should add, and that's it. We are adding what is in the what multiplicand register, right? So this one, right? So you realize that the same thing I copied because you are just multiplying by 1, and um we are adding it to this one. So when you add it to this one, you get this, right? Yes, and you realize that this one is -36, right? You can try to find it, and to do that, just find the two's complement of this one, right? So when you find the two's complement of this one, you get +36. But because it started with what, a 1, it means that what it is a negative number, right? And so realize that the both algorithm can kind of handle both negative and positive numbers, and this question is a proof to that. Now there is a third type called 3 boots encoding for boots algorithm. And that one is also pretty easy, right? It's just like the first two, except that this one you require more less cycles, right? So the previous one we required four. I think this one required only three, right? So it's the same thing. You convert and you realize that your multiplicand is what 1010. Because I'm still doing the previous one, and my multiply is 0110. So I append the zero, but this time I take the first three bits, right? And I go and check the encoding table. The encoding table is this one, as you can see. It says when it is what 100, you have to multiply by what -2 and add it. So that's what you are going to do. The first three bits we consider is 100, right? So you are going to multiply this by -2. But you see, multiplying by -2 is kind of hard. So what is usually the trick is that first left shift this one. You see, when you left shift a number, it's equivalent to multiplying by 2. So for example, if I have 0, 0, 1, right, and I left shift it, I'll come and get 0, 1, 0. Now this in decimal is what? 1. This in decimal is what? 2, right? So using that idea, we can do that quickly here. So what we do is that we will left shift this one once, right? So we will left shift it. It will come, when we left shift this one, our answer will be what? 1, 1, 1, 1, 0, 1, 0, 0, right? Now that's good. But after we flash shift this one once, it was -2, not 2. So we have to find the two's complement, right? And when you find the two's complement of this, you will come and get this. You come and get, I think, 0, 0, 0, 0, 1, 1, 0, 0, right? And that's what you see here, right? So that's the -2 we are seeing. Now, after we just add it to what is in the accumulator, and when we finish, this is the answer we get. Now, for the 3-bit boot encoding, instead of left shifting once, we left shift twice, right? So realize that this one, when you left shift it twice, you come and get this, right? So you left shift it twice. So for after each cycle, left shift it twice. Then you go to the next cycle. So the next cycle, the next three pair of bits is what? So we see, remember the previous one, which was 2 bits encoding, we're dropping only 1 bit. This one will be dropping 2 bits. So we'll drop the last 2 bits. And I will consider what? The next 3 bits, which is 011. So 011, right? That's what you see. And the encoding for 011 is that we should what? We should multiply by, like we should add by 2m. So that's what we are going to do. So we'll go and multiply this one by 2. And to multiply this one by 2, the rule says what? The trick is just left shift it once. And when you left shift it once, you get this one, right? Now when you add this one to what is already in the register, you get this answer, right? So that's for 2-bit and 3-bit encoding. Now you realize that this answer here, I think this minus 36, and this answer here, right, are the same, right? And that's because yes, it's the same question actually, and I'm solving using different encoding, right? So that's it.